Thanks. Okay, let's see if you can repeat that. Okay. Good. Good morning, everybody, and welcome to the second lecture in Distributed Databases 2. Oh, sorry, I forgot something. Just let me do that. It's my cool, whatever, we don't need that. Good. Today's lecture will be about distribution of data and partitioning of data. So why is that important? So let's rehash what we did last week. Last week we introduced what we will actually do in this lecture. And as I told you, this lecture will have three major topics. The first being traditional distributed databases, which we will do in detail this week, next week, and in 2 weeks. Then after that, we will do peer-to-peer systems. Peer-to-peer systems are not like traditional databases, so they don't have all these proper and nice features you would expect from a database, but instead focus heavily on scalability and ad hoc management of the network. So basically it's a very, very weak peer-to-peer database or database built of peers, so computers which can join and leave all the time and which have a shared common agenda. After we had a look at distributed databases, which are very traditional, and well, have a lot of features, and peer-to-peer systems which have a very limited feature set, we will then focus on cloud storage and NoSQL databases, which is basically the amalgamation between both. So you take some features from peer-to-peer systems, which is that flexibility, scalability, ad hoc joining of nodes and leaving of nodes, which now, of course, is not nodes joining and leaving, but it's nodes failing and breaking. So hardware which gets destroyed instead of just shut off. And we try to bring in some of the features we had in distributed databases back into our systems. So that is what we will do in the lecture overall. So basically we have something like that. So we have a trade-off between database features. So usually the more database features you require, the less elastic, the less flexible, the less scalable your system will be. And traditional distributed databases will be here in the lower left corner, while peer-to-peer systems are in the top right corner, and cloud systems can be anything in between. So they either could be very, very close to peer-to-peer systems, like, for example, Amazon Dynamo, which is basically a peer-to-peer network running in a single computational center, or they could be closer to distributed databases. So stuff like SAP HANA, for example, is not really a peer-to-peer system, not really a cloud system, but it's marketed as one. So HANA is more like a distributed database, so more traditional in its feature set. Good. This lecture, we will cover sharing architectures. So that's basically, we will discuss how systems can be classified into different sharing levels. Because what we're doing in all the lecture is we have the assumption that we have a data management system using multiple nodes, right? And now the question is, in between these nodes, how strong is the communication of these nodes? Do they share, well, for example, secondary storage? Do you have like network attached storage which can be accessed by every machine? Do you have even a storage area network, which is a super cool version of network attached storage? Or don't you have shared secondary memory? You could even have something like shared main memory, which is something extremely popular in the 60s and 70s and extremely popular since 2012 maybe. So it's one of these topics which re-emerges currently. So having shared main memory. And even if you do have shared main memory and or secondary memory, how strong is that bond? I mean, do we have slow network in between? Do we have fast network in between? And based on that, we have very different techniques and very different technologies we require to make the system, well, efficient and effective. After that, I mean, we don't really discuss in this lecture how these sharing architectures impact system design. That's something we will do in the coming weeks when we discuss the different systems, but it's something you always should keep in mind because, well, it really affects system design quite heavily. After that, we talk about fragmentation. Fragmentation is basically logically taking your data. So basically you take your data model and you cut it into little pieces with certain constraints and certain requirements. And after you have these pieces, the next question is, okay, what do you do with these pieces? Where do you put them? These are the problems of partitioning and allocation. So partitioning is a problem of deciding where to put the pieces, and allocation, well, how you push it to different machines and if you replicate them or not, these things. So in this lecture we will cover a very, very simple approach here, so just partitioning and allocation of relational data. And for distributed databases we try to minimize or don't use a lot of replication, because replication, as you all know probably from the introductory courses in databases, so replication and redundancy is quite frequently considered a bad thing for databases. And that includes also to a certain extent distributed databases. So if we have the same data multiple times, it means yes, it's more safe, because if you lose the one copy, you still have another copy. You have potentially higher performance because you can work with one copy and with the second copy at the same time, so you have higher read speeds. However, as soon as you come to writing, that becomes a problem, and replication will hurt you and cost you quite a lot. Therefore, here we also try to achieve a replication level as minimal as possible. And we will see later in peer-to-peer systems and cloud systems that there this paradigm shifts quite tremendously. So there you have like 20 replications, 15 replications, and in peer-to-peer systems sometimes even up to 1,000, 10,000, 20,000 replications. And that's because these systems actually don't care about writing. So mostly they are read-only systems, or they don't care if there are inconsistencies in writing. Good. Anyway, so what is the overall setting? The overall setting is we have a distributed database of, well, any design, which runs on several nodes. And now we can classify the designs of our database based on how these nodes can cooperate and can communicate with each other. And basically, what is interesting to us right now is if they share any storage. Might it be main memory or might it be secondary storage? If that storage and these nodes are located at the same geographic location, also a classical distributed database will be at one location. However, you can scale it out, and Jose will later do a detour into massive geographic replication and scaling out, which is very interesting. So there are some systems which rely on having nodes all over the world. And coupling, so basically how dense are nodes coupled. And basically what we have in distributed databases is looking like that. So we have the overclass of multi-node DBMS, so distributed database management systems. And first thing we can classify is if they share secondary storage or not. If you have shared secondary storage, then usually that means that all nodes are local, they are all in the same site, because sharing secondary storage over multiple sites does not really work well. And if somebody claims that he actually has shared secondary storage, then that's usually not correct, because usually when you have wide area network in between, it's actually an independent system which tries to act like it's a shared system. So shared secondary storage usually implies that you have a local geographic distribution. Now, the next interesting thing is how closely are the nodes coupled. If you have a close coupling, you call it a share everything system. So that includes shared main memory. And if you don't, then it's a shared disk system. Well, obviously you share the disks, like storage area network. Usually these things are used for, well, high performance computing, something like grid computing, big data centers in banks, companies, these things. Because the advantage of these systems is that, well, you can build very extensive feature sets quite easily. They are very flexible, they can be very powerful. Usually they don't scale that well. Yeah? And you buy that flexibility because, especially when you have shared disk, it basically also means that every node has access to all data stored anywhere on any disk, right? And if you don't share disks and you have multiple systems running on different locations or even around the world, that basically means that not every system, not every node can access all data. That has a lot of advantages, but also a lot of disadvantages. So basically, I mean, the obvious problem here is if you don't share secondary storage, you have to pay attention very closely on how you distribute data, where you to allocate data, and which node gets which data. Because, of course, every node can only access that data efficiently, which is located close to itself. And that's not suitable for all kinds of problems. So, for example, if you do something like Google does, like computing a web index, that works very well in a distributed fashion. So it's very easy to fragment that problem into smaller work packages which can be assigned to a certain node, and that node can work with that data more or less independently and just share the result. I think in lecture 12 or 13 we will do a whole lecture about how computation in a system like that will work. That's, for example, the map and reduce paradigm, which exploits heavily independent architectures, where you ship data to a certain node, you process it there, just on that node, and then ship away the end result. And you need a certain problem set, so you cannot apply it for any problem. So, for example, if you do weather modeling, weather forecast, for example, or modeling of stock markets, that becomes significantly more tricky. So a lot of scientific computations require actually very close coupling. And then these local systems might be a better choice. But that's something we will discuss in the next weeks anyway, just, as an outlook. Good. So, to the vocabulary. What kind of vocabulary do we use? Right now, we will introduce nodes, and we see a node as an independent computational unit. It's a single computational device. That word can have very different definitions based on the scope. So usually a node is one computer. However, when you have a look on a lower abstraction level, and from a database design perspective, a node could also be a single core within a multi-core computer. So it's a little bit hard to say exactly what is meant by the word node when you don't have the context in it, right? Because when we go to the lecture Relational Databases 2, we will discuss how you build a single thread database. And from that perspective, so from an architectural design perspective, even a multi-core system running on the single computer is already a distributed database with the CPU cores as nodes. So it's a computational device on whatever granularity. Then we have node groups. Node groups are nodes, a logical group of nodes which usually share a common agenda or which share a common hardware setup. So if we see as a node a single core in a CPU, a node group might be the actual computer. If we see a node as a single computer, a node group could be, computers in the same cluster. So computers which are very tightly interconnected with each other, which have a strong network connection, which share the same authority, the same agenda, something like that. So some shared organization. Then we have sites. Sites are usually node groups which are at the same location. And usually you assume that within a site you still have pretty good network connection. Of course, the network connection between nodes within a single node group is pretty good, so quite strong. Within a site, it's still strong, and in between sites, you assume there is a bad network. And that's something which we'll repeat quite frequently during the lecture. So different hierarchies of computational power, different hierarchies of network. So it's always about where is the fastest network. So, yeah.
Could it be that a node of a site is in another, or we have two nodes from the same site, and they are in different? No. We have, yeah. we have two nodes from two different sites.
And they're in the same node group.
Yeah.
That could happen. It depends on your definition of a node group. Node group is a logical group of nodes, right? And the grouping criteria, that's up to your application. So if you group your nodes based on their purpose, for example, like it happens in the Amazon data centers quite frequently, where you have multiple, for example, dynamo rings running in parallel, then you will assume that each dynamo ring, so it's multiple nodes which form one storage unit, and that thing is organized as a ring structure where you have a network connection, well, in a logical ring, and all nodes belonging to that dynamo ring are in one node group. But in order to be resistant to failure, Amazon, for example, distributes these things over multiple sites. So then you have a node group spanning multiple sites. You could also define it differently and say, okay, node group is everything which is in a single case. So it depends on, you look at things. Anyway, we have these three words, node, node group, sites, which can mean different things depending on the context. So always be a little bit careful there what's meant. Good. Let's start with this, shared everything architectures. Shared everything architectures, it's the first iteration of distributed databases. And these things go back to, well, the early ages of database research, which is the 60s. And they were designed for mainframe systems. So basically, you had a very strong machine. Back then, CPUs still used to be slower than memory, which is something which has changed a long, long time ago. So for quite a while now, CPUs are way faster than memory, which results in a lot of problems, actually. But back then, you had very slow CPUs and rather fast main memory, or comparably fast main memory, and you would connect multiple CPUs to a shared main memory and to a shared disk. That used to work quite well. Because, as I told you, back then CPUs were super slow and main memory was still way faster than CPUs. That could also mean that these CPUs could access the main memory more or less at will without getting in each other's way. Because, as we will see later, every time you access main memory from a CPU core, you have, at least in a distributed database, have to deal with problems like transaction management. So how can you prevent that one CPU changes data which is currently read by a different CPU? So you have to introduce locking protocol where you say, okay, that part of memory is now exclusively locked to that CPU, and this CPU has to wait until it's, freed up and stuff like that. That works very well when main memory is quite fast and CPUs have very small workloads. No? So that's something introduced in the 60s, but even in the 60s, you quickly had problems. So one problem is you get bottlenecks with the main memory. Even though the main memory is faster than CPUs, you get into this lock congestion threshold. So basically, when the CPUs take a lot of locks, then after a while, the system has to wait a lot. So locking data in a shared environment always brings in a big performance penalty. And scaling is therefore rather limited. But still, it's an architecture which started all the distributed database research, and a lot of theory is built for systems like these. And they fell out of favor, in the 80s, I would assume, where people switched to shared disk or shared nothing architectures. However, right now, these things are coming back because in the last years, we had a lot of advancement in hardware technology, and there are a lot of predictions for the future that the architecture of distributed databases or databases in general will quite considerably change in the next 5 years. So in between, I would say like 1975 until something like 2005, the architecture of databases didn't change a lot. So these things more or less stayed stable. However, in the next 5 years, we will see tremendous change here. And mostly that change is pushed and driven by hardware advancement. So since a couple of years, we do have stuff like remote direct memory access. So it's a technology which allows different computers to directly address and access the main memory of other systems in a computer cluster. So each node has its own main memory and directly over network can access other computers' main memory, usually using very high-speed network, something like infinity band. And that's basically all that deal with NUMA databases. So we will talk about NUMA in like 3 slides or something like that. So NUMA also is one of the design paradigms from the 60s, which nobody really cared about until, like 5 years ago. Good. So using these shared everything architectures, we nowadays build rather powerful parallel databases. Remember last week, parallel databases are those database systems which run in a fully homogeneous environment. We have one single database management system spanning multiple nodes with a central authority. Good. So shared everything architectures basically can come in different flavors, which can be classified how memory is integrated into these systems. Shared everything architectures do share secondary storage, they do share main memory. But how they share main memory and secondary storage, that can change. And basically we have 2 different approaches here. One is symmetric multiprocessor systems, the second one is non-uniform memory systems. I don't know if any one of you has interest in hardware design and CPU design, but in CPU design you also have the same 2 problems because it's more or less the same thing. So when the big manufacturers started building multi-core processors, which started I think in 2003, 2004, I don't know, something like that. So the first dual-core processors. And then now we have quad cores and octa cores, whatever, hexa cores, these things. The manufacturers of the chips themselves had to decide how to organize the chip, on the die. And basically, that's the time where these questions have become more important again. So both SMP and NUMA architectures did start out in the 60s, 70s, 80s, but now that's a big issue in CPU design as well. And for example, when you take CPUs from Intel, so the early Pentium multi-core processors and the early AMD multi-core processors, they had a different design paradigm. So for example, Intel opted more for something like symmetric multiprocessor systems, while AMD put a lot of emphasis on non-uniform memory access systems. So what does that mean? And what does that mean for us? If you have a symmetric multiprocessor system, now from an abstract level, not focusing on CPU cores, but a symmetric multiprocessor system in general is a system where you have multiple processing units which are homogeneous under a central control, and these systems share their main memory and their I/O over a centralized bus. Basically, it looks like that thing. You have CPUs. Each CPU may have its own cache, but then you have a big bus which has a shared main memory and shared I/O. Okay, that's symmetric multiprocessing. Why is it called symmetric? Well, it's called symmetric because every processing unit, which might be a CPU core, which might be a computer, which might be, depending on your granularity, any kind of thing, they all have the same access to data. So it doesn't matter if you put a job on CPU 1 or on CPU 2, it's the same. And the advantage of that is that it's very, very easy to do coding here, right? Because you don't have to care how to partition, how to distribute, and where to locate your data. So you just have to write your algorithm, which can assume there are multiple cores, and there's data, and data is accessible by each core in a similar fashion. So it's very easy for programming. And in the times, when we have a look on CPU architectures, all these multi-core architectures, they came in early 2000s. And back then, software was not really prepared for that. So a lot of software was running just on single threads. Now, if you had a multi-core CPU, it just means you could run multiple single-threaded applications in parallel. So a lot of people were rather disappointed in the beginning that performance of the systems did not double just because they had 2 CPUs or 2 cores. because software couldn't take advantage of it. So you could just run, well, you could do better multiprocessing or multithreading. But for a single application to actually take advantage for that, you had to adjust the code to a multiprocessing model. And that's very easy, or comparably easy, on SMP systems. Did any of you try Java multi-core programming already, like multithreading and stuff? No? Yeah, it's rather painful, isn't it? Yeah, so programming in Java, for example, for multiple cores, it's a very painful process because you have to deal with a lot of stuff like, okay, when do you synchronize, how to log data, when to free data, you have all these monitors, and it's a lot of work. But it's surprisingly easy in comparison to coding on NUMA architectures. NUMA architecture stands for non-uniform memory access, and as the name indicates, that means that the memory access to the main memory for different CPUs is not always the same. It's non-uniform. So basically, from a design perspective, that means you have multiple processing units. Here I just call them CPUs, which are connected to a central bus, and that bus is connected to a main memory unit. And then multiple of these groups are connected by the next bus to each other. That means for the first CPU here to access that main memory, that works rather well. That CPU also could access that main memory via that bus. I mean, that also would work. However, as you can see, that will be slower because you have an additional jump. So basically, for that architecture to be efficient, you need to design your algorithms in such a way that they can take advantage of the locality of data, right? So the best solution, or a good running algorithm here, would be that you partition data in a very, very clever fashion and move all the data which is needed by these CPUs in that main memory and all data which is used by this CPU into that main memory. And then have as little communication between those two groups as possible. Of course, you can communicate, but that will cost you. That's NUMA architectures. And yeah, we will see these two architectures on quite a lot of levels. We will have a similar architecture when we talk about computers connected via network. It's the same thing I just told you about node groups, right? So if you have multiple computers, just with a single CPU, let's assume, which are connected with very high-speed network within a single computational rack, and then put a storage area network directly at that rack, and then have multiple of these racks in parallel into a big storage center, that would be a NUMA architecture, right? Because each computer can access the storage area network connected to its own rack faster than the sun on different racks. When you look at it from a finer granularity on the CPU level, then you could have something like that. That's, for example, that. That's the layout and architecture of the AMD Bulldozer CPUs. That's the design AMD builds for the server processors. And as you can see here quite closely, I mean, you cannot read it obviously, but you can see it's a layout which is highly partitioned. So here you have one group, there you have one group, there you have one group, and there you have one group. And here you clearly see the NUMA architecture. You have one core here, that's first core, second core. These two cores share level 2 cache, so they have shared memory here, and a lot of shared processing units. Same thing here, core 3, core 4, they share a cache, they share processing units, 5, 6, 7, 8, and then you have a big shared level 3 cache. That's the same. It's again NUMA architecture, just on a smaller scale. And of course, if you try to program for that thing, you have to take care that you assign CPU responsibilities in such a way that these two CPUs can always work on their shared level 2 cache without ever requiring data in a different level 2 cache. Because what happens is, if that CPU would require data which is currently processed by a CPU over here, which is currently in that cache, then you have to propagate the data from that cache into main memory, from the main memory back into this cache, have to process it here, which means it's locked over there, you cannot continue working here, and then you have to push the changes back. It's really horrible. However, if you figure out a way how to do that efficiently, then you just put your data into that cache, and only these two CPUs have to synchronize over that cache, while you don't have to access the level 3 cache, and those CPUs can work by themselves. And that's basically also one of the problems behind multi-core architectures. And yeah, it's not really surprising that even nowadays, I don't know, when did the first Core 2 processor from Intel arrive? I think in 2005 or 6. And right now we are still at just 4 CPU cores for disk processors. I mean, there are some CPUs which have like 6 cores or 8 cores, but most still have 4 plus virtual cores. Why just only 4? Well, the reason behind that is that it's very difficult to scale beyond 4 processors or 4 cores without going to a really strict NUMA architecture. So all these cores, all these CPUs which have 16 cores, 32 cores, 128 cores, they will be NUMA architectures like that one, and which are harder to code and harder to use. And using that architecture, you have to adapt your code quite well in order to get good linear scaling. But you could get it. And yeah, that's one of the problems in processor design. Okay, questions up to here? Makes sense. Okay, shared everything, but even in shared everything, we have different levels on how shared stuff really is. Good. Next topic, shared disk architectures. After you decide that sharing main memory is too much effort anyway, because it requires a lot of work and a lot of synchronization, you could build shared disk architectures. That's basically the same problem we had before with the NUMA architectures in shared everything, just on the next level, right? It's if you share secondary storage or not. And a shared disk system, you have multiple nodes accessing the same hard drive, which is more or less the same problem like multiple CPU cores accessing the main memory, just on the next level, but still the same problem. And that works rather well if you have a tightly integrated environment. So for example, if your disk is within a single computer or within a storage area network. So in case you don't know, a storage area network is a specialized hardware technique which is usually sold for tremendous amount of money, where you have a high-speed network connection which directly connects to, well, disk RAID arrays. So basically the idea is you have multiple computers running in a computational center. All these things have only very tiny hard drives, so a couple of 100 gigabytes, and then you put a big storage rack into one corner, and that storage rack is connected with something like InfiniBand, so super expensive high-speed network, directly to the different nodes, and the nodes can mount in the hard drives in that storage area network as if they were local hard drives. So you build a cluster where the nodes don't have proper local hard drives just for, well, maintenance tasks, and all data is stored on the storage area network, and that's a local hard drive, more or less. It's just not local anymore. Good, that's a shared disk architecture. Good. Of course, we now have the same situation like in the symmetric multiprocessor versus NUMA. That shared storage area network can become a bottleneck quite quickly because everything which applied to shared main memory applies here too. You have to synchronize data, you have to have enough network resources available, you have to have enough bandwidth. Then, as will be the topic today in relational databases too, for those who also listen to that lecture, you have to deal with all the peculiarities and problems of hard drives themselves. I mean, nowadays it's not that bad anymore because nowadays we have these SSD disks, but like 1 or 2 years ago, still having a cluster made of hard drives was the state of the art. And hard drives have one of these really annoying problems that random accesses on a real hard drive are very, very slow. And if you have multiple computers requesting a random access from a hard drive, yeah, performance degrades very, very quickly. And one thing databases try to do, which is also a topic of relational databases too, is to minimize the number of random accesses to secondary storage and always try to read big sequential batches. Because a hard drive, you know, it's a spinning disk, it has an arm, you bring the arm to a certain position, then you wait until the disk rotates, and when the correct part is under the arm, you start reading, and then the disk rotates and you just continue reading, which works quite efficiently. And the slow part in a hard drive is always this moving the arm. And now if you have a database optimized to put the arm where it needs to be and then read a huge batch, that's fine. But as soon as you have multiple cores requesting a huge batch from the same hard drive, it degenerates into random accesses again. Now that's one of the problems you might get with these shared disk architectures on multinodes. You know, that all these optimizations you did on a hardware level don't work anymore. Therefore, quite quickly, we did the same thing for disk sharing like we did for NUMA architectures. So you just assume, okay, there are certain node groups, or maybe just a single node, and they have their own secondary storage. And of course, you can access data stored on different nodes, so secondary storage of other nodes. However, that will cost you because you have to go over network. These are basically shared nothing architectures. That's a database, for example, you build out of desktop PCs. So you have a hard drive, you have a CPU core, and they're connected by network. And again, you have the same problems like we just discussed in NUMA, right? You have to find an algorithm and a way on how to distribute that data in an efficient manner in such a way that you never need to access the data stored on different nodes, or very rarely need to access the data stored on different nodes, right? And this type of database was pushed quite heavily by companies like Google and Yahoo in the early 2000s, because if you do this architecture right and you have the right application, and not all applications are the right application for architecture like that, but if you do have the right application, then in theory you could achieve linear scaling. So linear scaling means you can just add, double the number of CPUs or nodes and performance doubles. Good, so basically it looks like that. You have CPUs, each with its own main memory and its own secondary memory, connected via network. Yeah, big question, which is the best architecture here? Yeah, you don't really know. It depends on your constraints. So for different applications, it might be different things. If you have a lot of money, well, you can more easily go to shared everything and shared disk environments. If you have to live on the cheap, then shared nothing architectures are usually always better. So you have a lot of advantages and disadvantages. So this is a chart. I mean, you have to take it very careful. It's not 100% correct. It always depends on how you implement these systems. So usually people considered shared disk systems easy to maintain. Data shipping within different nodes should be cheap because there's high performance network between these systems and they can read from the same main memory. Transaction cost should be cheap. What does transaction cost mean? Transaction cost means if you have a real database transaction. And database transactions, as you probably know, is a set of multiple database commands, so multiple reads and multiple inserts, which have to be executed under certain constraints. So for example, atomic and consistent and so on. So basically it means every node which takes part in a transaction has to communicate a lot with the other nodes. So you need locking, you need latching, you need some handshake protocols. So you need a lot of communications. And therefore, if you have a shared disk or shared everything architecture, that communication is cheap because it's fast. Within a single node, you only have moderate latency. Why is that? Because in a shared disk architecture, the connection between a disk and a node is not as fast as if you would connect the disk directly to the node. Now, therefore, only moderate latency there. Hardware costs are usually super high because you need specialized hardware. And, well, the maximum size there is, well, usually considered large for shared disk architectures. For shared everything architectures, I would consider it something like medium. You know, like, wow, 20 CPU cores or 50. You never know. But here you can go to, well, let's say 500 nodes. It's just numbers, you know, large. While for shared nothing architecture, you can go to extreme sizes. So it's quite easy to build a shared nothing architecture which contains thousands, 10,000, 20,000, a million nodes. Now, for example, the standard size for an Amazon Dynamo cluster is 10,000 nodes. That's surprisingly large. So 10,000 computers is one Dynamo ring. Good. So for the shared nothing architecture, we have a lot of red there. And that's a little bit tricky. So for example, in shared nothing architectures, data shipping is very expensive. Yes, true. Right? So if one node needs data which is located on a different node, it has to be shipped via a network which is super slow. And that being expensive is not that bad. It's only bad if you need to ship data. So if you use this system for an application and for an algorithm especially, where data shipping is avoided, that problem is not, well, that problem is more or less solved. Same with transaction costs. So most systems which rely on shared nothing architecture simply won't do transactions. So if your database doesn't support transactions, obviously you don't have a problem with transaction costs. And that's, you know, when you look at more modern databases like CouchDB and Cassandra, Bigtable, all these things, they don't have database transactions. Simple as that. And the reason is because if they had it, it would be super expensive. Therefore, you know, they just throw that feature out. Here's this data separate maintenance. It's also in red here, but that's something where you have to be very careful about. Usually, if you have a well-designed shared nothing architecture, these things can be self-maintained. So it's very simple for a shared nothing system to build an algorithm who manages the complete administration tasks by themselves without needing an administrator to do anything. That's usually not the case for shared disk systems. And there's no real technical reason for that. It's just, you know, how these products developed. So a lot of shared disk systems, that's traditional database products like ddb2, Oracle, and so on, where you assume that there is a database administrator, and companies and manufacturers are quite fond on putting responsibilities on administrators. While shared nothing architectures, it just doesn't work with administration. If you have 10,000 machines, there's no way that an administrator could take care of each machine individually. So it has to go automatically, which means from a human administrator perspective, these shared nothing architectures are extremely easy to administer because you just plug in a new machine and the system handles it. However, from the real costs, so what's happening then automatically, then the costs are rather high. So the algorithm require a lot of work. And in this system, you have a lot of traffic which is just shipping data to nodes, shipping messages to node, just to keep the thing running. Good. Yeah, I think that's, yeah.
What is meant by intranode parallel processing? I can figure out what internode parallel processing means, but what is intranode parallel processing and why is it very good with shared nothing? And
so intranode means parallel processing within a single node. Now, so not bridging multiple nodes. So, for example, you have a multi-core. So, okay. My viewpoint now is a node is a single computer, right? And if you have in your single computer, let's assume a multi-core CPU, then doing a multi-core processing within that CPU works very well in a shared nothing architecture because you have everything you need on that node. You have your hard disk, you have your main memory, and you have a multi-core CPU. That works very efficiently. Now, if you have to, let's assume your node has 4 cores, and you have an algorithm requiring 16 cores, which means you need 4 computers, which now work together. That works extremely bad. That's internode parallel processing, not deep red. Within one node, using your 4 cores, which are built in, works very well. Here, it's always like good and okay, because each node doesn't have its own secondary storage. So whatever you do, you still have to access the storage area network and read over network. Make sense? Yeah. Okay, good. Good. So I talked a lot about distributing data and putting data somewhere, which basically means now we have to deal with how do we actually distribute data somewhere. And there we have 2 different things which are tightly connected. One is fragmentation. Fragmentation is a technique of decomposing a given chunk of data into smaller disjunctive fragments. It's basically like taking a knife and cutting it apart in, well, multiple pieces. So after you fragment it, you can distribute your fragments to different nodes. Replication, that's a problem which goes hand in hand with that. If you have now your fragments from fragmentation, do you replicate these nodes or don't you? Replication means you do a copy of these fragments. And usually most databases will, well, just do it like that. So they do fragments and then they copy and replicate these fragments. In theory, you could of course do overlapping fragments, but that's something which is usually not done because it's super annoying to do and super annoying to manage. So it's very easy to assume that fragments are disjoint. By dropping this disjoint requirement, you get a lot of problems. So don't do that unless you know what you're doing. So usually it's fragmentation in disjunctive fragments and then replication. Good. Here the problem is, how big should your fragments be? Small fragments, big fragments. And if you have, let's assume a big table, which might look like that in 2D, and you take a knife and you want to cut it into fragments, what kind of fragments do you actually cut? Do you do stripes, like horizontal stripes or it's the other way, horizontal stripes or vertical stripes? Or do you do little, like rectangles, a small rectangle here, rectangles there, rectangles there? And again, of course, that's depending on the application which is better. So there are some distributed database management systems which do use certain default fragmentations. So for example, Bigtable, which we will do in lecture 12, that thing always does horizontal fragmentation. So it always cuts along horizontal stripes. And in some really bad cases, it even means that a single node will have just a single row of a big table. I mean, Bigtable obviously was designed to store really big tables, which means their table model. I mean, you all listen to introductory courses in relational databases where we do normalization, where we claim, okay, when you have a lot of attributes, do normalization, and then you have one small table which has foreign key requirements, to a second small table, and a third small table, and so on and so on. That's good data design. However, it requires you to join your data. So for example, if you take students at a university and you take exams, for example, good data design would be you have a student record, then you have exam records, and you have a table in between where you say, okay, this student took that exam and got that grade, right? So you would have 3 tables. And now if you would need a list of single students on all the exam results, you would need to do a lot of joins. This is how we teach it in relational databases 1. And which works reasonably well. It's a very good and clean data design. However, you need to join in stuff. And what a lot of distributed databases do, Bigtable for example, say, okay, all this joining, that's too expensive, it's too complicated, we can't do it in a heavily distributed environment. So we just denormalize it massively. And you just use a single freakishly large table for your whole database. So just do all your university management and all your exams, blah, whatever students in the single freakishly large table. So basically the Bigtable would look like, okay, all student data like name, address, and so on. And then there would be columns for each potential lecture a student might take or might not take. And if a student does take an exam and you want to narrow down the grade, then you just fill in that part. And well, so you have a huge table which is largely filled by null values. Well, this is how Bigtable works. It's a horrible data model, but they have pretty good reasons why it should be done like that. And if you now cut that thing horizontally, in the worst case, it can even happen that one of these rows is so large that you will need a whole node just to store a single row. So for example, for Bigtable, you have a maximum of, I think, 200 gigabyte per row. So a single row can have 200 gigabyte. And if they have smaller machines which have a hard drive of 300 gigabyte, then just a single row fits on a single machine. And that's not rare that this happens. So for example, if you put satellite images in it, so for example, for Google Maps, yeah, that happens rather quickly. Okay? So fragmentation, how big are fragments? Do you just cut rows? Do you just cut columns or little rectangles? Then, allocation. Where do you put these things? To which node do you assign them? And after you assign the to node, do you do a replica? And now that problem is very tightly interconnected to what we talked about in the last, I'm so slow, in the last 3/4 hour. So you always want to put data close to the processing unit which will later process the data, right? And that's maybe one of the major things you should keep in mind after this whole lecture cycle. Always try to exploit locality in your data design. Now, for distributed databases, as we will do them right now and for the next 3 weeks, that's very challenging because you don't know upfront where your data is actually needed. And we will do next week predictive models and statistic models which try to predict where data should be. And of course, that doesn't work well. And if we go to these really cool distributed databases, stuff like Bigtable, they just go around this problem and they just claim, okay, so for example, in a Bigtable environment and MapReduce environment, you just claim, okay, every node is only allowed to work on its local data and that's it. And there's just no, interconnection, there's no intra-node parallel processing, you just disallow these things. And yeah, problem solved. If you just remove the feature, you don't have the problem anymore. But yeah, as a rule of thumb, put the data there where it's needed and where it's done. So basically, you end up with something like that. You have a big relation, which you cut into little pieces, so fragments. Relation, fragments, that's a process of fragmentation. We will always assume in this lecture that these fragments are disjoint. That's not a requirement, it's a requirement for this lecture. In theory, you could build a system where they are not disjoint, but it's easier with disjoint, and then you allocate it to different nodes, and there you can see that you can replicate certain things, or, you don't replicate certain things. Good. So, more formally, what does that mean? Okay, you have a big relation R, R for relation, and you do a fragmentation, which results into fragmentation of R, which consists of multiple relations R1 until Rn, which obey certain rules. What are the rules which we need here? Now, for one, they are all very obvious. Completeness rule. It means if you somehow puzzle together the fragments, you shouldn't lose data. So basically, all these fragments should contain all data, and you should be able to reconstruct your original relation after composing it. Then the disjointness rule, that one is actually not a requirement, but it makes your life significantly easier. Fragments shouldn't overlap. So if you do, an intersect between the fragments, the intersection should be empty. And reconstruction rule, if you reconstruct the relation, it should preserve all data and properties, constraints, like foreign key constraints, and so on, which were in the original relation. So it's basically the same like completeness, just also considering the constraints. So straightforward. You shouldn't lose anything during fragmentation, and it should be disjoint. Now, how might that look like? So for example, here, that's an example that I will reuse quite frequently in the next 2 or 3 lectures. It's a creek database about entities in Greek mythology, and there you could have like gods and titans and heroes and monsters, and you can have locations and cities, like Athens and Sparta, and you can have certain artifacts which belong into a city and into to an entity. So, for example, like the temple of Poseidon in where was it? I don't know. I think Athens or something. And here you can that's funny. Actually, you can't because the beamer is cutting it. No. Oh yeah, you can. So here you can see you can join that table with that table, and now this table with that table, and that one can be joined with that one, right? And now we have an data model with 3 foreign key relations. So between, I used to have a pen. Here it is. So you can join it along these lines. Good. Now, let's just assume that it doesn't fit on a single computer, so we can partition it. Simplest thing to do is horizontal partitioning. You just take a table, cut it horizontally into stripes. And then you have these fragments, and you can distribute them to different machines and allocate them to different machines. Now the question is, how can you decide on how to fragment horizontally? Well, that depends. Now, you can do a lot of different things there. You could either assume that there are certain ranges. So, for example, all cities with less than 100,000 inhabitants go to one fragment, and those with more go to a second fragment. Now, if you do that, the big question is, which ranges do you choose? So in the early database designs, that was a decision made by the administrator, which could work out rather well, or, well, sometimes it didn't. Then you could provide value lists. That's also something more traditional. In more modern systems, you have predictive algorithms which will predict which would be a good cutting point based on distribution of data, based on the query load. I mean, it's a pretty bad problem, actually. No? It's not enough, at least for an optimal solution, to just have a look on the data. You also need to have a look on how the data is used. Now, if you know, for example, for cities, so if you have more inhabitants than 100,000, you're considered a major city. Below that, you're not, eine Großstadt in German. And if you have a task which frequently does stuff only with Großstädte, and with major cities, and, well, ignoring everything which is not a major city, it might be a very good idea to cut with 100,000 and put all major cities in one fragment and all those which are not in another. But in order to do that, you need a certain domain knowledge. And of course, this domain knowledge is very hard to come by automatically. So that's an administrator decision. Now, the range partitions, value list, based on some attributes of the data itself. The third option here, hash values, that's something which is extremely popular with peer-to-peer systems and shared nothing architecture systems which scale very large. So here you just claim, whatever, I don't care about semantics. I don't care what it actually means to fragment my data. I just fragment it randomly, and I'm just choosing a proper random technique to do it, which guarantees me certain things. And one way of doing it, you're deciding on an attribute, and you create a hash value of that attribute, and based on the hash value, you put it into a certain fragment. And that's a trick, for example, in distributed hash tables. The name already implies what's happening here. It's a hash table in a distributed environment, which is a technique for building peer-to-peer systems. You just take, for example, the name of a file. It's very popular in file sharing, for example. So imagine yourself a file sharing system like eDonkey, for example, was using that, or Kazaa, if you still remember that. And based on the file name, you create a hash, and then based on the hash, you put the file to a given computer. Well, not the file, but the file reference. And the good thing about hashing is that hashing algorithms have a lot of requirements and properties they fulfill. So, for example, a hashing algorithm will have a defined range. So, for example, SHA-1 hashing algorithm, uses the full range of 128 bits, that's right. No, 255, I think. Whatever, one of those. So it uses the whole hash range. And it uniformly distributes any input on that hash range. That's pretty cool, right? So as you can see, if you have a hash algorithm which uniformly distributes anything you put in to a certain range, you already have a very basic version of load balancing. So you can more or less assume that the resulting partitions and fragments are all more or less balanced and of a similar size, at least in a very simple theory. Now, later we will see that that simple theory will not really hold because people are interested in some things more than in others. So, for example, to stick with the file sharing example, it's nice that you can, for example, distribute all pirated MP3s more or less uniformly to all computers you have available. However, as you all know, there are a lot of songs nobody cares about, right? There are certain songs which are currently very hot and everybody wants to have a copy of these, while there's a huge long tail of things, you know, whatever, nobody cares. So doing a fragmentation like that sounds in theory better than it will be in reality. But it's a very simple technique. So if you have no clue how to fragment your data, why not hashing it? It will work good enough. And that's, by the way, one of the core design principles in databases anyway. Don't try to find the best solution because the best solution will be super complicated and slow anyway. Just make a good solution which is good enough. Those of you who do relational databases too, I think you will hear that like a dozen of times. Like, oh, you could do this index better, but you know what, it would take too much work. This is good enough. You just leave it as it is. So, yeah, database people are very practical with that things. Good. Of course, if we cut in horizontal stripes by whatever techniques, we still have to apply our three rules. So it should be horizontal complete. If we cut it horizontally, how do you reconstruct different fragments into an overall relation? Yeah, you do a union. Because, right, it's the same relation, just cut into different stripes, you do a union, and in the end, the original relation should be result. Then, how do you test the horizontal disjointness rules? Yes, you just do an intersection on all these fragments, and each intersection between any possible combination of fragments should be empty. Then they are obviously disjoint. So, horizontal reconstruction rule, so it's not enough to just keep all your data. You should also keep all your constraints, so all primary keys still must remain unique, all foreign keys still must be preserved. Well, that's trivially true because you didn't change anything, right? So horizontal fragmentation is very simple in that respect. Of course, you could also do vertical partitioning. So you just take your knife and you don't cut horizontally, you cut vertically. Why should that be useful, or how would that work? So if we, for example, take a look at our cities table, we had three attributes like the name of the city, the ID of the city, the type of the city, and the location of the city. So which area is it in? And you could just cut out the location and put that into an own table. As you can see here, I did replicate the ID here, right? So I just didn't take my knife and cut through the table, because if I would have done that, I would have violated the completeness rule and reconstruction rule, because if I just cut out that location attribute, how should I know how to reconstruct the table afterwards, right? Because then I would just have only locations without knowing which location belongs to which city. Therefore, I have to replicate the primary key in order to be able to reconstruct it. So for example, then the completeness rule is, every attribute still should be there, and I can reconstruct it by joining the different, so now it's not union, it's joining. So if I now join all these fragments with each other, then I can completely reconstruct the original fragments and original table, as long as I did replicate the primary keys. So that's the thing I need to do here. Good. So which of these two is better? So why should you need vertical partitioning? A lot of systems decide on horizontal partitioning. A lot of systems decide on vertical partitioning. But why? Yeah, just try.
One question about the tables.
Yeah.
We have to duplicate the CID.
Yes.
Because we slice the table.
Yes.
Vertical. But isn't the original table that normalization? Because the location isn't. I mean, there might be a city which is in the same location.
Yes. So for example, I think we have, no, not in this example, but I mean, just assume that there are additional attributes too. So it's not just location, so this table goes on for quite a while and also goes on here for quite a while.
But I would think if I have to duplicate ID.
Yes, you have to duplicate the ID.
Yeah, then I could have normalized the database better.
You could have. However, I mean, this is a bad example of database anyway, but just let's assume it's a student. No? It's not cities and location, it's a student, and it's something like first name, last name, address. Well, that's perfectly normalized. Now it's actually not, you could take out the address. But let's take telephone number and matricle number. So for this example, yes, you could just do a better normalization, and in a better normalized schema, that would be its own table. That's right. But if you have a large table, which for whatever reason you cannot normalize farther, this might be because it's already perfectly normalized, or it could be because you're a system like Bigtable, which cannot do normalization anyway because it has no support for joins. Then you have that problem. And here, with the rows and the columns, it's a very interesting discussion. I mean, we are now on the lecture distributed databases, and we are questioning ourselves, you know, should I cut my data horizontally or vertically? Which makes in this context a lot of sense. But that question reappears in so many different topics. So for example, if you do the lecture relational databases too, so traditional design of traditional databases, there you will see that everything in traditional databases is organized by rows. You have table spaces, and there you actually have the same problems, right? You have, for example, on hard drives. On hard drives, you have certain coherent chunks of data which have a certain size, so blocks, for example. So a hard drive block is usually 4,000 kilobyte, so significantly larger than an actual data record, and you have to put multiple records into a single hard drive block. And you abstract from these hard drive blocks into larger blocks, so buffer memory blocks. Now the question is, if you have large hard drive blocks and even larger buffer memory blocks, what do you put into these blocks? Do you put in rows? Because, I mean, your whole table won't fit into a single block. So somehow you have to fragment your data to fit into that block. Same problem like we have, right? Do you put in rows, or do you put in columns, or do you put in, single values? Same problem there. It's not exclusive to distributed databases. And in normal relational databases like MySQL, ddb2, you usually choose rows. Why is that? You usually choose row because you assume that when you build a normal business application, like a management system running in Prüfungsamt or something like that, or normal office application like an accounting software, you assume that usually the user is interested in all the data which belongs to a single record. Now, for a student, for example, you're always interested in all the data which belongs to a student, and you're rarely interested in a certain attribute of all people, right? And therefore, you put all data which is likely used together into one storage unit, so the whole record, okay, which makes a lot of sense. However, if you now go to the lecture Data Warehouses, which will be tomorrow, Data Warehouses is a lecture about data storage systems for data analytics. So it's systems, for example, for company management, where you have a distributed database, for example, at Aldi. You're boss of Aldi, right? And you have like 10 Aldi shops per city, for example. Each of them share a single data center, and every product sold at Aldi, for example, is tracked in that database. And you always have a record, okay, shop 1 sells this article for that price at that date in that location, right? And you put that into a huge database. So you have a gigantic, massive table of transaction data sold at location. And now you're interested in toothbrushes. How many toothbrushes are sold grouped by a city? Or which is the most popular? No, that's even better. What is the most popular toothbrush brand in each single city? That's something you might be interested in order to optimize your thing. How would that work? You would access all records where a toothbrush was sold and group them by the location. You don't care about all the other data which might be in a row. So if there's a big row with each transaction, there might be something like some ID, some recipe number, some whatever. You're not interested in that. So you're only interested in grouping by location and selecting by toothbrush. So you're interested in columns, which means that these analytic storages, they organize everything in columns. They don't use rows as a storage unit, but they use columns because they have a different application. And the same two things, of course, apply here, right? So depending on what your use case might be, very different things might be a good idea. Good. Very good example, for example, when vertical partitioning is more feasible is when you need summary statistics, aggregate statistics, or if some attributes are very rarely accessed but are very large. Now, so for example, in the medical information systems, if you have patient records and you have one row where you put something like an X-ray image, and you don't access that X-ray image every time you access a patient, then that would be a thing where you would easily do vertical partitioning. Okay? Good. So which one is best depends on your use case and your application, and of course on how much effort you want to spend in order to optimize that system. So if you don't care, just do hashing on horizontal partitioning. That works well enough. Good. Of course, you can combine both. Of course, you can do hybrid partitioning, which does certain horizontal partitions and vertical partitions. And if you have fragments like that, you do for vertical partitioning duplication of the IDs, and then you horizontally cut. And if you want to reconstruct, of course, you join that part with that part. So you do a join here, join there, then you have horizontal slices again, and then you just take the whole thing and make a union of it, and then you reconstruct it. Good. Now, we fragmented our data into disjoint fragments. Now we have to replicate and allocate them. To which machine? Well, to those machines where it's most likely needed, however that might work. And you may replicate your fragments, so you can store them multiple times. The advantage of that obviously is, yes, you can do parallel processing on it. Yes, you don't lose data when you just lose a fragment because there's still a copy around. Disadvantage is, if you update these fragments, how do you handle inconsistencies? So if you have multiple copies of the same fragments containing certain rows, what do you do if somebody doesn't update? Do you actually lock all copies and then push the update to each copy and just prevent anybody of reading them in between? That would work. That would prevent anybody of reading a dirty copy. Or don't you care about that? So for example, if you don't do anything in such an environment, you could have two fragments of the same part of a table. You update it here, and while you update that fragment, a second processor might come and read that data here, which is already outdated. And after it's read here, you copy your change over there. The processor does something with the outdated data it just read and then tries to write it back, and basically all your data is dirty. So either the change is overwritten and now it's inconsistent, or it used stale data, so whatever. So you have a problem there. And you can approach this problem on very different techniques. So here in the first part of the lecture on distributed databases, we assume every type of problem which might arise from replication, it's horribly bad and we have to prevent it at any cost. So it's a very pessimistic approach. So problems are horrible, they need to be avoided and prevented. We need rules to prevent dirty reads, to prevent dirty writes, to prevent inconsistency, because that's all horribly bad. And yeah, we spend a lot of effort on these problems. If you don't care, like for example, like Amazon does or Google does for their distributed systems, yeah, then whatever. Then just people can read dirty, write dirty, you just propagate changes after a while, and well, if they're out of date, it doesn't really matter. That's also a solution to the problem. So not caring is a pretty good solution to a lot of things. Yeah, I mean, it's again a trade-off. So what to do? If you prevent problems, that will be, yeah. Good, again, wonderful table. What are the potential problems? So here, what are the things you could do? We have query processing. Query processing, that will be the topic of next week. So this is, given a query which may span multiple fragments, how easy is it to actually execute that query? That's for full replication super easy, because full replication means every node has a full copy of all data. That's full replication. So if you have 10 nodes, everything is copied 10 times, and everything is available locally, so you can execute your query locally. Very cool. Directory management. Directory management is the problem of knowing where your data is and locating your data. So basically it means you have a directory, you look up in the directory, I need that data piece, and the directory tells you, oh, it's there, and then you go there and find it. It's very easy with full replication because, well, it's local. You will find it directly on your own hard drive. Concurrency control. That is multiple CPUs or multiple processors using the same data. That's in full replication moderately easy because you know that every node has the data, and the simplest solution to concurrency control and transaction control is just locking everything, which is very bad for performance but easy to do. If you go for partial replication, for example, it's very tricky because you have to figure out, okay, where's the data? Can I lock it? Do I need to lock it? Is it actually required? And so on and so on. It's very annoying. While if you do full partitioning, so full partitioning means you have every fragment only once, that's super easy because you have only a single copy of each data, so you don't care about concurrency and transaction control. But then, of course, for partial replication, partitioning, directory management, and query processing gets more annoying and more complicated because you have to ship queries quite a lot. You have to figure out where data is located, which is not very easy. Reliability, that is how likely is it that you lose data? And of course, if you have 100 copies of everything, it's very unlikely that you lose your data because there are tons of copies. If you have every data only once, yeah, that's bad. Then you lose it when it's gone. Good. Then performance potential. We have potential here for parallel queries, which of course is very high if you have full replication, because that means everybody has all data available. You can run queries in parallel quite easily. However, that means that parallel updates are horribly bad. Again, that's a problem I was just discussing. If you have 100 copies of something and you change one copy, how do you publish that change? It's a horrible problem. And of course, that problem is very easy when you just have a single copy, right? Then, how realistic is it that you actually do full replication or full partitioning? Yeah, well, not very so. So usually most systems will end up with replicating important parts and quite frequently, and replicating some parts less often when they are not that often needed. So for example, in systems like Google Bigtable, every fragment by default is replicated 3 times because they claim that the probability that all 3 fragments or all 3 replica are lost at the same time is very low, because you have a certain time for repairing a machine. Now, so for example, you have 3 copies, 1 machine breaks, 1 copy goes away, then some guy will start running into the data center, will replace the computer. In that time, maybe a second copy might disappear, but as soon as a guy repairs the computer, the 1 single remaining copy will start replicating itself again, and it will self-heal. By the way, that's the same thing we will be doing in relational databases too. After this lecture, we will talk about RAID storage. RAID storage is the same thing. And it's surprising how many stuff here always is the same thing. It's same problems, same solutions all the time in all the lectures. It's quite funny to see. Good. That's quite realistic that you do a healthy mix between replication and partitioning. So how efficient is it from a storage perspective? Yeah, full replication, obviously, is very inefficient. If you store everything once, that's very efficient, obviously. But yeah, usually you go with that middle part because that's a good trade-off between full replication and full partitioning. And we will have the same discussion again when it comes to peer-to-peer networks. So in peer-to-peer networks later, we will also do replication, full replication versus no replication, and there we will do network connections. So how many connections are in between nodes? Will there be only 1 connection, like in certain systems, or full connections? And there it's quite interesting that depending on your use case, you actually can do the full range of things. So for example, Amazon in their Dynamo systems do use full network connectivity, which is the network equivalent of full replication. I mean, it's not full replication of data, but it's full replication of network connections. That works quite nice, while in a real file-sharing peer-to-peer systems, you would go for, well, a partitioning approach. Again, same discussion in 10 weeks, just with networks. Good. Maybe we should do 5 minutes of breaks here, or 10. 10 is good, right? 10 minutes. Then we go on with partitioning techniques. Manage. Okay, so for the remaining part of the lecture, I just skipped over what's coming now. And it's quite interesting what happens in this lecture now, because we are talking about replication, and as it seems, a lot of the things we already discussed in the last hour is replicated in the following slides. So basically, we have 2 things remaining. One is an interesting detour of Jose about how Yahoo Peanuts does geo-replication, which is very, very interesting. And that's a wrong lecture, by the way. While we are talking about how you actually do vertical and horizontal partitioning and fragmentation. And a lot of these things I already mentioned. So what I will do now is I will go over the slides and pick out these parts which are interesting and which we did not cover already in the last hour, and jump and skip some other slides. Just that you know, these slides are there that you at home can better prepare for the exam, and that you have a better script, so don't wonder when I'm saying like, okay, we talked about that already and skipping over something. Good. So we talked about that there is fragmentation, and that we have horizontal fragmentation, vertical fragmentation, and hybrid fragmentation. Now, the problem is, how does it work? And why should you fragment in one way or the other? And of course, it all relies on what you try to achieve with your system. So you first, when you design a system, have to think about what the system is supposed to do in the end. And that's a very interesting design change. So traditionally, databases were intended to be one-size-fits-all systems. So the claim was you buy an Oracle database, and that Oracle database will do any application you throw at it. It will be perfect for everything. Which, was partially true for quite a while, but which stops being true right now, and which is, especially for distributed systems, definitely not the case anymore. Because distributed systems, you can optimize for a lot of different things. One thing you could optimize for is minimize query and update costs, assuming that you have data which can be sharded and fragmented quite easily. That's one thing you could optimize for. Another thing could be maximize the possible degree of parallelization. So assuming you have queries, and you have very complicated queries, so something like analytical queries, which run for 10 hours, and such a query which runs for 10 hours should be executed in parallel so that you can run it in 1 hour or half an hour, right? That could be a goal. Another goal could be you have 10,000 queries per second, and your single system cannot handle, and you need a distributed system to handle your query load. So you don't actually care what happens to parallelize a single query within, but you care about parallelizing multiple queries. You might care about durability. You might care about having a system which never fails, whatever happens, including earthquakes and fires and floodings and exploding nuclear power plants and whatever. And of course, all these design goals will imply a different system design. They will imply a different fragmentation style. They will imply different allocation techniques. And one size definitely does not fit all. And that's one of the important changes of distributed databases. But right now we have this fragmentation allocation. If you look at the problem of figuring out a good fragmentation and allocation from an abstract point of view, you will see that there are different approaches how to solve the problem. You could either do qualitative and quantitative approaches. That's actually the same thing we are doing also in our ddb2. So qualitative means you just have a look on the data, you have a look on the schema, and based on what you see on the schema, you have certain rules of thumb, so certain heuristics which have proven themselves, combine them with your domain knowledge about what you expect to happen, and use that information to devise a fragmentation and allocation yourself. Right? That could be done at design time. That might be stuff like, okay, we have our students, and for each student there's a big picture attached to the record. We don't need that picture quite frequently, so we do a vertical fragmentation that all raw data according for a student comes into one fragment, while all the pictures go to another fragment. And if I actually need the picture and the student data at the same time, then I'm joining, which doesn't happen that often. That would be a qualitative approach. I'm just assuming certain things about the system and do it. And that's the same thing we will see when it comes to query optimization. Now, query optimization will be a topic in 2 weeks, where we decide on next week, I think, where we decide on actually how to execute a query and which rules to apply to an operator tree, how to execute it. You could do that qualitatively. So for query optimization, for example, you take the SQL, translate it to relational algebra. So in case you wondered why we are teaching the relational algebra, that's why, in order to do query optimization. And then we have certain rules we can apply to that operator tree, which transform a suboptimal operator tree into a better version. Better version, not the optimal version, right? That would be qualitative approach. Quantitative approach here is I actually do statistics. So I observe the running system and I observe what is happening in the system, and from that I try to extrapolate what I should do to optimize the system while it's working. That's a very cool technique which can be done either very naively and easily with little effect, but where you can devise extremely complicated algorithms, and that's an area of still ongoing research. So self-tuning and self-optimizing system, that's the thing to go, because one property you want to have with modern systems is that you need as little administration overhead as possible. So you don't want to pay human administrators. So the more the system can do by itself, the better it is. Right? So this is qualitative versus quantitative. Quantitative approaches are usually stronger, but they are more difficult to implement. Now, that next sentence, that's super interesting. The main goal is to partition in such a way that all applications perform optimally. Well, that won't work at all, ever, right? So your actual goal is to build a setup which performs good enough again, and which doesn't really destroy your applications, because it can never be optimal for all applications. It just doesn't work. Different applications have different requirements, which are quite often antagonistic to each other. So sometimes you require that, and sometimes you require the complete opposite of it, and it just contradicts. Right? And also, usually figuring out the optimal solution is so expensive that you waste more time and effort on actually optimizing than on executing. Now that's, for example, one of the big problems of query optimization. If you optimize longer than it just would take to execute the query as is, well, it's a bad deal. Same applies here. Good. So what we do need is, we do need simple techniques which will result in something which is good enough for most applications. Good. And yeah, so we need certain heuristics to figure out how to partition our data. And yeah, these heuristics, well, first we have to clarify for ourselves what it is we want to do. Do we want to optimize for parallel access, for low communication costs, for high replication, for whatever it is, and then depending on our goal, we can decide on a certain heuristic. So for example, when we optimize for parallel access, then we should distribute tuples in such a way that we can have a very balanced query workload, and that queries can work locally as much as possible, which, yeah, requires that we have high update costs and that updates become extremely difficult. We could optimize for low communication costs in order to avoid shipping, so all kinds of things. Now, high availability, that will be a topic for Jose later. So we want our data to be available at all geographic locations. That's a surprisingly interesting problem, by the way. Because if you consider a real distributed global application, something like Facebook, something like Google, something like, these things. The network connection between two distant parts of the world can be quite slow. So for example, I was in Japan for 2 years, and the best ping I could get to a server in Germany was something like 300 milliseconds. And that's quite a lot. I mean, 300, so yeah, I used to play League of Legends quite a lot before I went to Japan. After I arrived in Japan, I figured out that that won't work with my old account because it's just so insanely slow that it just doesn't work, because the Europe servers are obviously in Europe. And when I'm in Japan, it just doesn't work. It's so slow, you will lose. And that applies to data distribution too, right? So if you're looking at a global application, you also have to optimize your data that it's at that place where it's needed. And when the same piece of data is needed at multiple places, then you have to replicate it, that it's really available there. Now, often you don't know what is needed where. So that was, for example, one of the early achievements YouTube did. Now, YouTube was one of these platforms which had to fight a lot with these popularity effects. Where somebody did a stupid video of its cat eating a toast or something, and nobody cares, and the mother looked at the video like, oh, it's a cat eating the toast, maybe the brother, and then somebody put it on Reddit, and suddenly that thing goes viral, and every moron on the world wants to see that cat eating a toast, right? And these people use streaming video. It's HD streaming, which is super expensive network-wide, and you cannot stream that video from a single server to all places around the world. Right? Doesn't work. Not with these network latencies. So you have dynamically to realize, oh my God, that video is going viral, and while it's going viral, replicates that video to all locations where, well, it's popular. And that's not necessarily worldwide. I mean, if I do a funny video in German, I don't think that it will be very popular in the United States, for example. So no point in replicating it to there. Well, with videos and YouTube, it works nicely. Well, of course, videos don't change, so what will happen there is you see there's a surging demand, you start replicating that video. After a while, you will have a lot of replica of that thing. Then you will realize nobody cares about that cut anymore, which usually happens the next day or 2 days later, and then you start destroying the replica again. That's okay. The people working for YouTube know that. They designed the system exactly for that workload. They know stuff surges in popularity and then falls down. And that's very important that they know. They need to optimize their system for that purpose. Good thing is, videos don't change. Your cat video stays your cat video. You don't have to edit it. The only thing which happens is that people might comment on it or upvote it, which isn't that hard. I mean, for that you would need a different system. So likely the database storing the comments and the upvotes is a different system than the system, not likely. Definitely it's a different system than the one streaming the videos. Good, just for geo-replication. If now the videos would indeed change, and you would indeed do thousands of replica of that video which is edited in real time, then you are in deep trouble. And there are some applications who actually have that problem. That's super annoying. Now, that's, for example, the problem of social media games becoming popular. So we have a social game, so stuff like Farmville, for example, which is quite good because Farmville is limited to your local friends. So you know more or less how to shard and how to fragment your data, but it's quite tricky. So running, for example, global games is really hard. And one problem of dealing with geo-replication and data required everywhere is sharding. I already mentioned that. Sharding is a technique, I think we don't cover it explicitly in the slides, therefore I'm just telling you. Sharding is a technique where you take your data model and cut it into real independent pieces, which can be run fully independent of each other. And within these pieces, you do certain replication. Certain things are in each piece, but each piece can run its own copy and they don't interconnect. That's, for example, something you would, the League of Legends example is a pretty good one. You have certain shards. You have the Europe shard, you have the North America shard, you have the Pacific shard, and the Korea shard, which are not connected to each other, and each shard runs independently. If you can do that, that's pretty good for performance, and that helps you a lot with your geodata. And it's quite interesting, though, for example, Google also does certain type of sharding. However, it's a transparent sharding. So, for example, if you have Google Mail, that will be in a local shard, so your Google Mail stuff is not shipped from the United States, it's located in a data center in Europe. But as soon as it realizes that you move, and you move, for example, to another country, it will realize that and it will push your data from one shard to a different shard, or after a while. That's pretty interesting. I think, we will cover that later too. Good. So it's always about your application. Then, we can talk about horizontal partitioning. There's obviously a very simple way of doing horizontal partition. We covered that already. You partition by a given value set. You partition by certain predicates. You can partition by a hash value. Then we have derived horizontal partitioning. That's when you have joins. Basically, that means if you have, for example, a student record and you have a second table where you have addresses, and you always do join between student has address, typical 3-table layout with an intermediate table, address table, student table. And of course, as soon as you partition the student table into horizontal partitions, and all students starting with A go to that machine, all students starting with B go to that machine, it would be a very, very wise idea to also partition the address table and put all addresses of students belonging into that machine also to that machine. Non-surprising, because you want to have local joins. That's called derived partitioning and vertical partitioning. Good, how can you do primary horizontal partitioning? Either manually or automatic at design time or automatic at runtime. And usually you use a certain predicate. So you decide on a predicate like we did before, like major cities with more than 100,000 inhabitants go to one fragment, the others to the other. Quite easy. Same can be done automatically. There you could design very simple techniques like hash partitioning. Or you could do it during runtime. And that's the more interesting part. That's what I talked before. automatically tuning a system at runtime. Big advantage, you don't have administrative overhead. It automatically decides, based on usage statistics, what to do with the things. However, that's very difficult to do. And that's what good cloud storage systems, that's apart from bad ones, doing that in a quite efficient manner. So we will talk about that in the context of peer-to-peer systems when it comes to reliability and load balancing in peer-to-peer, where based on the query load, stuff gets replicated and fragmented automatically. It's a very interesting topic, and there's still no definite solution, but it's something you should strive for. Good. During design time, simple techniques for doing it is using attributes and predicates of your table. So for example, what you could do is you take your table. So this is, for example, the table of, we have seen before, with artifacts which have a certain level of grandiosity. So how great and impressive they are. And we look at which predicates you could find based on the queries you would expect. So you're expecting two types of queries. So for example, select entities where name is a certain value, or select artifacts where the grandiosity is in between. And based on that expected query load, you decide on a partitioning and design time. Good. So we can, I would actually suggest you have a look at that at home. I think we shouldn't waste time on that right now, because it's actually not really that tricky and surprisingly boring to tell you right now. Good. Let's look for something interesting, because we really have to hurry up. Good. Okay, let's try that one. That's good. Okay, horizontal partitioning. I told you that it's very important that you can do joins locally. As soon if you have a common join, like for example, joining a student with its address or his address, and that has to jump over multiple nodes, then this is a problem, right? And what you should do there is you should bring those parts of a join which are frequently used to the same node, so that they can be executed without shipping any data. So how you could do that is by using a very informal approach. I mean, implementing that thing requires a little bit additional effort, but informally it works like that. You build a graph where each fragment is a node. And every time when you need a join, you will put it into the graph, and then you try to minimize that. So that's, for example, a very good join graph. Now, so you have here fragments of R, so the first relation. You have here fragments of S, and what you try to do is you have those fragments S1, S2, S3, S4. And this means that you only need to join stuff in R1 with stuff in R2, S1. That's, for example, when you have all students starting with A in one fragment and all addresses of all students starting in A in another fragment. It's enough to join these two fragments. That would be very good. That would be an optimal join graph, because then you could put fragments of R1 and fragments of S1 to the same machine, to the same node. Same applies to the others. So that would be a total join graph. Total join graph is something you want to prevent all the time, because that means that you have to join every fragment of R1 with every fragment for S1. That's something you want to avoid. So if you end up with a join graph like that, you did something wrong, or your data is just not very well suited for distribution. That one here is perfectly suited for share nothing architecture, because you can just put it to on machines. For this one here, if your data really looks like that, a shared nothing system will be very hard to do, because it means that you have a lot of communication. For that one here, if your data is really like that, a shared everything and or shared disk system is definitely more beneficial to you. Now the big question is if you end up with a graph like that, is it because you did a bad job at fragmentation, or is it really because, yeah, that's the way your data is? No? Usually most applications will end up with something like that, a partition join graph. So where you have certain partitions which are required frequently and others aren't. So for example, it's enough to join R1 with S3 and R1 with S1, and that usually will do for most queries. That's okay. Then you need to have a minimal amount of query shipping. Good. But let's have a closer look on certain techniques for doing partitioning. A very good thing is, I mentioned that already, is horizontal partitioning using hashes. And that's super popular in cloud storage systems and peer-to-peer systems, because in these systems, you just decide on an attribute, which is a defining label. So for example, the name of the song or ID of something, hash it, and based on the hash, you put it to a certain node. So for example, in this example, we have the song Purple Rain. We decide on the name as an identifier, so we take purple name, hash it, and let's assume it ends up as a hash with 3483. And then we have multiple nodes here, right? So these are nodes. And each node is responsible for a certain range of data, right? That one is responsible from 611 to the hash of 709, and so on and so on. And based on the hash, you put the song to a given node, in that case to that one. Now, and you see something interesting here. This node and that node is the same node, so this is not a list, it's a ring, right? So we have these nodes. So what is that line? Lines here are network connections. So what we will do later in our peer-to-peer systems is that if you distribute stuff by hash, it's surprisingly tricky to find the things afterwards. How would you find Purple Rain in this setting? Just think about it for a moment. In order to find Purple Rain again, what would I need to do? I would need to hash Purple Rain, right? And then I would need to figure out on which computer is Purple Rain actually. And here on my chart, it looks deceptively simple. So here it looks like, okay, 3583, that's obviously here, right? It's very simple because I put these labels here. But now if we assume that we have 10,000 machines, how do we know which machine is responsible for which data? And that's the directory problem I was talking about an hour ago, right? So knowing which machine is responsible for what data and which things I can find where. And that's a problem we will spend quite a lot of time on peer-to-peer systems because, yeah?
Can we use something like with networks or routing, I don't have it, move on, I don't have it, move on, I don't
yes,
have it, move on, okay,
exactly.
I have it.
Yes, that's exactly the thing you would do. However, I mean, what kind of routing do you use? So there's a whole branch of research focusing on what kind of routing will end up with what complexity. So for example, if you have a ring like that, you will easily see that you could start here. Do you have it? No. Do you have it? No. Do you have it? No. Do you have it? Do you have it? Do you have it? And that's a linear search, right? So if you have 10,000 machines, worst case you have to ask, well, 10,000 machines. If you have a 1 million machine, worst case you have to ask 1 million machines. And that's something you want to improve, of course. So you find clever tricks to make that better, right? So that's just an outlook what we'll do in 3 weeks, finding proper routing techniques for that problem. Good. Yeah, hash partitioning. If we use hash partitioning, which is a very powerful technique, which is very popular, advantages, it works automatically. You don't need any design terminology. You don't have to think about it. It's super easy to implement. You basically can ignore any kind of semantic knowledge. In quite a lot of cases, it will result into a natural type of load balancing, at least in theory. In practice, well, it won't work that well, but at least in theory, it should work quite okay. And you should get a rather stable performance. Now that is because we talked about that already, that hash functions distribute uniformly over the whole hash range. So basically each node here should have an equal number of MP3 files on them. At disadvantages is basically the same thing like the advantages. You don't use semantic knowledge, right? So semantic knowledge you might have and which might have provided you a lot of insights and better results, you're skipping that. Good, and you're ignoring the actual query load. So in very simple hash-based partitioning, what you should do is actually during runtime repartition everything and redistributing everything based on system performance, like my YouTube example. Now, when you realize it's going viral, yeah, you have to improve it. Good. Yeah, vertical partitioning. Vertical partitioning is a little bit more tricky than horizontal partitioning because you have to still be able to recompose the fragments. And for recomposing the fragments, you have to duplicate the primary key. We have seen that already. And you have a hard time here for finding an optimal solution. So vertical partitioning is usually done using heuristics. And you have two types of heuristics usually. The one is grouping heuristics, the other is splitting heuristics. And by grouping heuristics, you just replicate the primary key and then group. It's a top-down approach, a bottom-up approach. By splitting heuristics is a top-down approach. So by splitting, you just start with the whole relation, and you just have a look on the relation and decide on where it's best to cut. And then for each of your fragments, you replicate the primary key. So that usually works rather well. So I think that's a part we will be skipping right now. And we will go to that one here. That's quite interesting. So we can learn something here. Good. And that's how you could do horizontal partitioning and vertical partition in a semi-autonomous way. Because what we can do in vertical partitioning is we can have, what data do we actually need to do a proper vertical and horizontal combined partitioning? We should have a look on our data, so how our data looks like, and we should have a look on how our queries will look like. We can do that at design time by doing a projection, what kind of queries we will need. In a lot of systems, that's quite trivial because it's predefined which queries are there. So it's rather rare that you have a system where any type of query can come in. Usually this is just research systems or analytic query systems where people can define queries at runtimes. So for example, for Amazon, you know what queries are there. You know you can list stuff by category. You have something like, okay, show me everything a certain customer has in a shopping cart. It's always the same queries. It's not like you could freely define queries there. So based on the queries you have a look on which attributes do these queries actually use. And then based on the expected usage of attributes, you group attributes and rows in such a way that queries can be executed as efficiently as possible. Okay? So how will that look in more detail? For doing that, we use multiple matrices. So we use an attribute usage matrix. That is a matrix which has the queries which are expected in the systems as rows. And for each attribute, which are the columns in that matrix, if the query uses the attribute or not. So basically it looks like, later slides. Good. And then we have the attribute affinity matrix. That is how closely related are attributes. And what we want to find is we want to find attributes which are usually accessed together. If we find out that in our typical expected query loads, certain sets of attributes are always used together, then these attributes should go into one fragment, while the others should go in another fragment. Okay? So that you can execute one type of queries on one fragment and the other type of queries on the other fragments. So how could you do that? Let's go back to our example tables with the cities and artifacts in Greece. One query we might expect is find the political type of a city with a given ID. Query would be select type from cities where city ID is, whatever. Now in that table we have 4 attributes, the city ID, we have the type, and we have location and name. And what that query uses is the ID, there, and we have the type, there. So that query uses A1 and A3. So second query could be find the names and types of all cities, so the like CNAME and type from all cities. Then we could have like find all cities in a given area, or how many democratic cities are in a given area, and so on and so on and so on. And then the next thing is we should consider how frequent are these queries, because it's quite common for a lot of systems that a very limited set of queries produces the highest amount of work. So for example, Amazon, most people on an Amazon web shop will actually browse. And the most common query most likely is, give me a list of products belonging to that category, maybe with that filter. That will be like 80% of all things Amazon does. Okay, sometimes they actually sell something, but that's, not as common as browsing. So we use that knowledge later. Now we build that matrix, and for each query, now that's my query 1, 2, 3, 4, 5, we just note down in that matrix which attributes they use. So very simple matrix. If a query uses an attribute, we put a 1 into the matrix, and if a query doesn't use an attribute, we put a 0. Simple matrix. So now we want to construct this attribute affinity matrix. That is a matrix which shows us how related two attributes are in order to put related attributes into one fragment, and so that everything which is closely related ends up in the same fragment. Now we bring in the frequency of queries. We bring in the statistics. And we just count how frequently in a given time interval a certain query is executed. And we realized after observing the system that query 1 is executed 45 times, query 2 is rather rare, 5 times, query 3 is super popular, 75 times, and query 4 only 3 times. That is what that vector means. So, next thing we could do is, now we compute the affinity of each attribute. And the affinity matrix has all attributes as rows and all attributes as common, and each number in that affinity matrix represents on how likely it is that that attribute or those two attributes are accessed together in the same query, right? So how can we do that? Now, that's actually rather simple. We just go through all queries, and if there's a query which uses both attributes, here, if we find any query which uses both attributes, then we sum up the frequency of that query, right? And we do that for every row. So what does that actually mean? It means summed over all 4 queries we had, attribute 1 is accessed 45 times together with attribute 1. Why is that? What does that mean? That basically means attribute 1 was only used in query 1. Query 1 was accessed 45 times. Therefore, 45 times attribute 1 was used alone. Because if we go back here, we see attribute affinity matrix. Attribute 1 is only used in query 1. Attribute 2 is used in query 2 and query 3. So if we now have a look at attribute 2 here, attribute 2 is used 80 times conjointly with attribute 2, also with itself. That's number of times query 2 and query 3 were executed, 80 times. Now, attribute 2 is used 5 times together with attribute 3, because the combination of attribute 2 and attribute 3 was only used in, I think, query 4 it was, which was executed 5 times. And attribute 2 is used 75 times together with attribute 4. Well, that is in queries, we can see that here, 2 and 4 here. query 3 uses 2 and 4 at the same time. Okay? You get it? Attribute affinity matrix makes sense. So, what could we use it for? Well, if you now have this attribute affinity matrix, we do a very, very simple trick. We do clustering, right? You can just apply a simple matrix clustering approach there and try to find parts of that matrix which should belong together. And it actually doesn't really matter which cluster algorithm you use, so any cluster algorithm for matrices should do. And what the result should be that we reorganize columns and rows in such a way that elements which are similar should be close together. And the result will be a clustered affinity matrix. So it would look like that. So after you apply that algorithm, it actually doesn't really matter what's happening there in detail. So if you're really interested, there is a chapter about that in one of the books. It's mentioned on the slide. So if you want to read in detail, yeah, of course you're invited to. But basically what it does, it just reorganizes the columns and slides. And the results will be like that we reorganize A1 and then A3 and then A2 and then A4. And we will see here that A1 is quite frequently accessed together with A3, that A1 is frequently, or A3 frequently accessed with A1, no, vice versa, it's symmetric. And that A2 and A4 are quite frequently accessed together. Good. So now we can do a very simple fragmentation. Problem is A1 is a primary key. So a natural fragmentation would be that thing here. Just put A1 and A3 together into one fragment and A2 and A4 together in another fragment. That would be the thing you should naively do. However, I1 is a primary key. You will need it in any fragment. So which ends up with two clusters. One cluster is just a cluster containing A3. So you have one fragment, A3 and A1, which would cover that part. So all queries using A1 and A3, and there are quite a lot of them, could work exclusively on that single fragment without needing to access the other fragment. The second fragment you should create is A2 and A4, and it has to include also A1, because that's a primary key. And the second number of queries can be executed only on, or mostly on, that fragment. And only very rare queries, I think that was query 2 and 3, would require both fragments. Right? So most queries can be executed either on that fragment alone or on that fragment alone. On only very rarely you need to ship data in between and use both fragments. So the resulting partition would be something like that. So you have the ID, then you have the name of the city and the location, and in the second fragment you can just have the IDs and the the political type. Both fragments are separated and would work quite well. Good.
Do you want to start the tool next week?
No, we still have 15 minutes. So much for skipping over slides. Yeah.
Okay.
I mean, if really people come in 15 minutes or in 10
Yeah, we
minutes,
can.
we
We just. Okay. Yeah. That's fine. Yeah. So now imagine that we have decided which fragmentation strategy to use. So the next question that we need to solve is, so where are we going to allocate in a computer network each of these fragments? And this is actually a very old problem if you think only about file allocation. If you are interested, you can just look up at the paper that we mentioned here in the slide. But actually, for distributed databases, that's another story. So what we would like to do now is to just try to answer the question of where is my data. And we're trying to think at a web scale. So this is a real, very cool work from research project to a really production environment, 2011. And this is about, imagine that you're one of these big companies on the web. So imagine that you are Facebook, you're Twitter, and in this case, you're Yahoo. This is a work which was actually done with Yahoo. And the question that they were trying to ask was the following. So if I know that for a web application that is running on Yahoo, if I know that a record is only accessed in Europe, so the question is, why would I care about taking one of my replicas to, for instance, Asia, to my data center in Asia? Why would I do that? Or if there is a record that I only access in America, why would I have a replica in Europe? So this was the main topic of the framework that they developed to answer the question of where should I put my data? And this is the thing that we would like to talk about in the next few minutes. But before, so we need to know what's behind this approach. And behind it's what is called, and this is a very cool thing to read, a massive parallel and geographically distributed database system for Yahoo web applications. That's Peanuts, which means Platform for Nimble Universal Table Storage. I will give you a glimpse of what's the architecture. It's just a sketch. I will not go into the whole architecture, just to clarify how it works, to motivate the work behind the idea of where is my data or where I should put my data. And so it goes like this. So in Peanuts, data is organized in tables. But the cool thing about this is that you have basically a key value store. So you have a key, you have some metadata about the record, and you have, I don't know if you can see it from the slide, but this is basically the value of each record is a JSON format, which means that you have a very flexible schema. Are you familiar with JSON format? Yes, right, okay. So, and you have organized the data in fragments, but in horizontal fragments, which makes sense. I mean, that's why we talked before about when it makes sense to do it. So in a web scale, these guys solved the problem saying, wait, let's do horizontal fragments. And they call these fragments tablets. And in each tablet, you have up to 1 gigabyte of data. And you point for each table, you decompose in several fragments. That's what we have here. And then for each one, you know in which storage unit you will allocate the data. But the cool thing about this approach is that you actually have two kinds of tables. So you have order tables, which means that your keys are already ordered by the values of the keys. And you have hashed tables as well, which means that you just apply a function, a hash function, over the value of the key of the value, and that's the way that you organize your data. And you have all these nice things of inserting, deleting, but one of the things that make Peanuts very interesting to look at is that they were one of the first in providing range access to records. And that was something very unique if you think about key value stores, and was not actually a trivial thing to do, but it's actually in the system. And how it works, you have a table controller which communicates to several routers, so they replicate in which storage unit is located your data. So this is, as I said, it's just a brief overview of how it works to understand what was the motivation behind this idea of answering the question of where is my data. But you have indexes, you have views, all these nice things, and this was one of the key issues regarding this project, geographic replication. So how it works, so just think about a social network application and how they deal with the fact that you have to replicate updates to the different data centers. And how they solve the problem is, in Peanuts, you have the following thing. You have the notion of a timeline consistency, which means that, for instance, so Alice is at home, is sleeping, and she updates that now she's awake, and now that she's at work. And you have to ensure that this is serialized. I mean, if you have your data replicated in several data centers, the order in these updates should be just in the way that the timeline specifies. So Alice will not be happy if the system were unable to do this. Why? Because at some point, even though in this kind of web scale applications, you kind of relax things, this is something that you don't want to relax, because Alice will not be happy if, because you don't care about these things, she will be appearing like at work, but actually sleeping in some nodes on the replicas. So that's why Peanut says, okay, let's do this timeline consistency. And in that way, that means that every single record has a master, has somebody who says, okay, if you are going to update, there's one who is responsible for carrying the update and then propagating the update by a publication subscribing policy, which means that for every record, for every master that you have, you subscribe to be notified when you will be receiving the update. And this is done asynchronously. That's how it works, and this is all we need to talk about and come back to our question of where is my data, or where should I put my data? So one of the things that they were facing at Yahoo was the following. So when you, well, how many of you have actually signed for a Yahoo account? Not too many? So there is, yeah. So, but it's fun, because when you do that, there's one thing that you have to agree on, which is the terms of use of the service. And in this thing, there is actually something that tells you about where your data will be stored. And they were facing some things, some legal issues, saying, well, if I'm in a country where, because of the policies of my country, my data should remain in my country. So how will you impose these constraints to your replica system? This is something that was missing from Peanut's design, and it was actually one of the motivations to do this kind of work. So this is one of the main questions they were trying to answer. So how can I impose these kind of legal issues? And how about the minimum number of copies that I want to have for every single fragment? So there is some data that is so critical that I don't really want to miss to have a minimum of copies. How can I do that? Given that, just imagine the system was already running and they were facing these problems. So how do you incorporate these two things to a system that is actually running? And the other thing is, okay, let's try to improve the way that we deal with bandwidth. And there are two issues here. One is the replication bandwidth. That means that, remember that when we want to update, there is one guy who is responsible for performing this update. But that means that if I receive that, I will be propagating this request. And that cost, that's bandwidth. And the other one is this forward. I didn't mention that at the beginning, but the records that you have in Peanuts, they are basically two kinds of records. One of them is where you actually have the key and your data, and the other one is you only have your metadata. I know that this exists, and I can point you to where to look at, but I don't have the value. So that means that this is another cost that you have to minimize if you want to improve the way that people should be looking at the applications, because you have also some things that you want to guarantee in your system. One of them might be that 90 or maybe 90% of the requests are satisfied in less than 50 milliseconds. That's something that is not that easy to satisfy, and it was actually not built in Peanuts until they came up with this idea. So what was the solution? So they came up with, it's a very cool term, but it's actually a very simple idea, which reminds that sometimes very complex problems are actually very simple to look at and to solve them. So they come up with the idea of selective replication. So they will do it to record, but they will respect the policies constraints that we mentioned before. And so what they did, they add a new layer, a new abstract layer over the system, and they come up with a language, a very high-level language to specify the constraints that they were looking at. So you have minimum copies for a given replica of data. You have a sort of list of where, in which data centers do you want your data, and you have a list of where you don't want your data to be. So this is the things that they came up. And if you see, this is one example of a rule. This is at a table label. So if you have the table users, then you value your users, right? I mean, you don't want to lose them in your system. So let's say that I want the minimum of 2 copies, and that will suffice for the application. And you were able to specify the priority of this constraint, which as the number goes up, it's more important. So if they are overlapping, the one which has the highest priority will remain as the rule to look for. But you can do this even better. So you have table level, but you have field level. So again, we're looking at the users table, but if the home location of the user is France, then, well, I like French people, so I want to have 3 copies of my data, right? So these guys, they don't seem to like to each other. I mean, history shows that something like that happens. So you will say, this is I don't want my data, my French users, I don't want them to be replicated in the data centers that are in the US. So you fix the priority to 1, which means that regarding to the previous one, this has a priority if you have users from France. So this is a very high abstraction layer over a system that it was already running, that was very needed, very powerful to do. In the paper, they show the algorithms to implement this, but what they achieve is to give developers this thing that is very easy to understand, and it solved all the things that they were having troubles with. And the other thing is, so now that I do know how to specify these policies, how to establish the minimum number of copies that I want, so the question is, so how to decide where to put my data? So they came up with 2 approaches. One is the static approach, when you have at a record level, you specify the record level and you specify all the constraints that you have over that record. And based on these values, you will decide where to put the replica. So, should we stop? No? I like 10 more minutes, maybe, or should we stop? Okay, yeah, that's fine. We'll start this next week. Okay.
Maybe just summarize the organization.
So basically.
But they have up to now.
Yeah. Okay. So basically, one of the things that they innovate was the following: this dynamic idea of placement. So instead, remember in the lecture, it was mentioned that you collect some statistics of the queries and the attributes. If you think at web scale, that is really, really impossible to do if you measure the advantage of doing it. So what they came up with was, okay, simple things. If I want to dynamically place my replicas, 2 things that I can do. I assume that if you want to read at a place, this reading will come up more. So with these simple things, they managed to create a very powerful and dynamic placement of the records over the data centers. Basically, that's it. And we can just...
Okay. And we will
Yeah.
continue that next week.
Yeah.
So basically what we do next week. Next week we will cover how we actually do queries in these systems. So Jose gets full time to do his, finish
okay.
his detour, and we will talk about how to actually ship queries and how to distribute query in such an environment. So, and then we will be in time, I hope. Sorry. So have a nice week until then.
Anything that I can do?
No. That was good. Sorry for taking your
Yeah, no,
time.
that's okay. I think it was very important to.
Yeah, boo, whatever.